Hello everyone. The topic of this lecture is subgroup of a cyclic group. So first we define a cyclic group. A multiplicative group G is said to be cyclic if for any x belongs to G, there exists an element A belongs to G such that x is e raised to power k for some integer k. In this case, A is called a generator of G, and we write G is generated by A. The identity element E is given by A0. If it is an additive group, it is not a multiplicative group. Multiplicative means here group under multiplication, means E into A is A square, A into A is A cube, in this way. But there may be some group, additive group also. So in case of additive group, that system will be like this: A plus A equal to A instead of A square. A plus A plus A is 3A. So in this way, if G is a cyclic group, additive group generated by A, then for any x belongs to G, x equal Ka for some integer k. So in place of power e raised to power k, we will write x equal Ka. This is k times multiplication of A. This is k times, and here k times addition. K times addition. So this is a difference in multiplicative cyclic group and additive cyclic group. For example, the set of integer is a cyclic group under addition, and this cyclic group is generated by two elements, 1 and -1. It has only two generators. So for any one can observe that for any integer n is this, so it can be written as n equal n into 1 or minus n into minus 1. That's why, so every integer can be expressed as n times of 1 or minus n times of minus 1. Another example we can take, there is a group, if G is a collection of fourth root of unity, iota and minus iota. Here iota square is -1. So we can see that if for any x belongs to G, x is iota raised to power k for some integer k. Like if 1 is, 1 can be written as iota raised to power 4, -1 is written as iota square, and iota is iota raised to power 1, and minus iota is iota raised to power 3. So every element of this can be expressed as iota raised to power 1, iota raised to power 2, 3, iota raised to power 4, or sometime we say iota raised to power 0. This is 1. So this is a cyclic group, and this also a generator of this minus iota. One can verify easily that. Now let H be any subgroup. H be any subgroup of a cyclic group G generated by A. If H contains only identity element, then H is also a cyclic subgroup. Of G, because H contains only one element, so every element of H is a power of some power of identity. So if H not equal to E, then some element X belongs to H, or you can say H belongs to H, such that H is different from identity. We want to show that H is a cyclic subgroup. To show here, H is a cyclic subgroup of G. We means to find an element of H, that every element of H is in some power of that element. So we start with this. So let H belongs to H be any element. Then H belongs to G, as H is containing G. So that implies H is e raised to power n for some integer n. Because H belongs to G and G is a cyclic group, so H will be some power of A. Now by well ordering principle, well ordering principle means the set of every subset of natural number has a least element. So we can think about the least power, least positive integer n, such that H, this e raised to power that number belongs to H. So by least positive, by well ordering principle, we can determine here there exists a least positive integer t, such that Et belongs to H. Clearly As does not belongs to H for any this S lying from 1 to t minus 1. This is very natural to assume that, because E belongs to G and H belongs to H. So if this is a group G and this is H, so there are some power of A here, A square here, A cube here. So one stage there will be A raised to power something n here, A t here, then A raised to power t here. So A raised to power t plus 1 may be there. So because H is a subset of G, so element naturally every element of G is in some power of t, some power of A. So element of H also may be in some power of A. So we can assume that there must be a least positive integer t such that At belongs to H. If it is 1, t is 1, then obviously E is a generator of G and lying in H, and therefore that will be H will be G in this case. So by well ordering principle we have obtained a least positive integer t that will play an important role to describing the generator. In fact, we claim that h is generated by this et, like we can say b, where b equal to at. Okay, we claim that. So as we have already seen that now h equal e raised to power n belongs to h, and b is e raised to power t belongs to h. So there is a two integers are there, and n and t. So two positive integer n and t, such that now by division algorithm there exist two integers q and r, such that q and r such that n equal qt plus r, 0 less than r less than t, by definition of division algorithm. Now h equal an can be written as aqt plus r, and then aqt into ar, and this at raised to power q ar. That implies ar equal h bq, where b minus q, where b is e raised to power t belongs to h and h belongs to h. So this right hand side belongs to this right hand side, since h is a subgroup, so h b minus q belongs to h by closure property and the criteria of a subgroup. So this belongs to h. That implies ar belongs to h with this condition, which is not possible if r not equal to 0, because we have taken t as a least positive integer, such that we have taken that as does not belongs to h for any this. So because of this condition, so if s is non-zero, then r is non-zero, then it will satisfy this condition, and that will be not possible. So that implies r equal to 0, and that implies n equal qt. So this is, so from this here, from this we get from this expression here, h is e raised to power n and e raised to power qt and b raised to power q. So that implies so that implies every element of h is some power of b, that is h is generated by b, and this is at. So this proves that h is a cyclic subgroup. So this proves that, proving this, every subgroup of a cyclic group is cyclic. Now we can think about some example on and some application of this result, some applications of this result. First of all, if we applications, if we let G with a set of integer, and this is generated by this and this. Now take G is a set of integer, and this is additive group, additive cyclic group. Z is a cyclic group. So by the above result, if H is any subgroup of Z, then H must be is also a cyclic group, and there exists a least positive integer K such that least positive integer K such that H is generated by K, and being a additive subgroup, it means that Kn belongs to integer. So structure of this, thus any cyclic, any subgroup of Z is of the form Kn and this, and we write it, this is Kz for some integer K, for some integer K. If K is 1 in particularly, that will be a Z. So now we know that since Z is an abelian group and H equal NZ and K equal MZ be its subgroups, then H plus K equal K plus H. H plus K equal K plus H, and that implies H plus K is a subgroup of Z. In multiplicative group, we say that HK is a subgroup if and only if HK equal KH. And in case of addition, we write in this form. So because we are dealing with additive group, set of integer is a group under addition, and it is cyclic group, so it is abelian also. So this is a subgroup of this. So that implies H plus K equal dz for some integer t, that will be GCD of nm. This can be verified easily, that is nz plus mz is equal to dz, where d is GCD of nm. This can be proved by using some elementary number theory, so this is not a very difficult situation, because we know that d is GCD of mn. If we take d is the GCD of mn, so then d can be written as mx plus ny for some integer x and y. So it is clearly d belongs to this, and vice versa if we take. So it can be proved by using some elementary number theory. Also further we consider intersection of these two. H intersection K is also a subgroup of Z, so that will also be a cyclic subgroup, means this is NZ intersection mz is a cyclic subgroup, so it will be all of the type LZ, where L is the LCM of Mn. So we can see that from this study here, we see that every subgroup of a cyclic group is cyclic. Okay, from this fact we came to know that every subgroup of Z is of the type kz for some integer k, and third, if h equal nz, k equal mz are subgroups of Z, then h plus k and h intersection k are subgroups of Z, and that implies h plus k and h intersection k are cyclic subgroups. And so there exist integers, you can say positive integer d and l, such that h plus k, that this is equal to nz plus mz, this is equal dz, d is GCD of mn, and h intersection k is nz plus z intersection mz, lz, l is a LCM of mn.